Hello everyone, and welcome to this video where I'll be taking you through a sample question on the objective determine the derivative of a parametrically defined curve with linear functions. So in this video, I'm going to be going through a question presented at Knewton.com in their Knewton Alta program. I'll be in instructor mode, so you won't be seeing this as a student if you're doing this in Knewton Alta. Hopefully watching me go through this one problem here will help you out with other problems, on the same objective that are similar in the future. All right, so here we are. Now I know the answers, like I said, I'm in this instructor mode, so the answers are presented. I'm going to show you how they got there, or at least one way to get there. And of course, you can always, if you're somewhat familiar with the topic, try pausing the video, working it out yourself, and then come back, watch me work through it, compare your work to mine, and see how well you're grasping the material, how well you're doing. So here we're asked to determine the derivative of the parametrically defined curve represented by the equations x of t equals 2t plus 7 and y of t equals negative 2t minus 1. So the x and y coordinate of our locations depend on this parameter t, and as it was mentioned in the objective title, both of these functions are, linear functions of t. But still, we're asked to find, dy over dx. Remember, this was the derivative of y with respect to x, the slope of the tangent line to the rectangular equations curve if we were to eliminate the parameter and write a rectangular equation with just x and y and find, y prime or dy over dx. That's what this represents, right? The slope of the tangent line at any point on this curve. So let's go to some paper here. So again, the parametric equations were, x of t was 2t plus 7 and y of t is negative 2t minus 1. Now you may recall, hopefully you recall, I'm assuming you've seen something like this related to the derivative of a function from calculus 1. When we're given, y equals, some function of x, say, so say I have a rectangular equation where y is dependent upon x, then the first derivative, which was labeled, y prime, or the instantaneous rate of change in y with respect to x, right? Like a change in y or a change in x at an instant. So that's why it's the d instead of the delta, right? Delta is coming up here in a second. And how we found this back in, calculus 1 was we took the change in y over some interval, right? Delta y divided by the change in x, right? Change in y over some interval where x changes a certain amount. So here delta x is not 0, right? So I'm going from one x value to another x value. Look at the y coordinates, calculate their change. Now this was the slope of a secant line, and what we did after that was we had delta x get closer and closer to 0. So you might remember this notation, right? We said, what's the limit as delta x approached 0? As that change in x got closer to 0, what was the rate of change of y with respect to x approaching? That was the first derivative back in Calc 1. Well, this is all well and good when y is a function of x, right? When we have a rectangular equation, just x and y, not this x and y are functions of t, right? Some parameter t. Well, we can fix this pretty easily. To get it in terms of t's here, you have this parameter t be used. Let's see what happens at different values of t, and then what happens as a change in t goes to 0. So I'll ask that question, right? What happens as, oops, I already have the word as there, sorry. As delta t goes to 0, right? So if I have a one value of t, I'm at one location on the curve, right? Say there's t equals a, and if I'm at another value of t, right, a different value of t, right? So delta t is not 0, the change in t is not 0. Say t equals b, and then there's some curve being traced out. Now, this is not the curve that we're given. We're given linear equations. So you're going to see when I put this up later, these will just trace out a straight line. So the line going through these 2 points, right, here's the line going through these 2 points here when, say t equals a and t equals b. This has a delta y to it, a change in y, and then it also has a delta x, right? A change in x coordinates, horizontal change, vertical change. Well, hopefully this makes sense that if delta t goes to 0, right? If I have delta t go to 0, that means, say I fix this point here, and then I have delta t approach 0. So we're going to be going toward moving this point along this curve. I should have moved it along the curve, but have point from t equals b move closer and closer and closer to this point here. So maybe we're here even, right, where delta t is really tiny. And if I have t equals a and then a very, very tiny delta t, we're getting a tangent line at t equals a derivative. Now, what I was saying is I hope this makes sense that when the change in t shrinks, the change in x shrinks. You see how when t equals b here, if I move the value of t closer to a, the point on the curve is closer to this point here when t equals a, so delta x is also approaching 0. So as, delta t approaches 0, delta x will also approach 0, right, on a continuous curve, differentiable as well. Now, so that's going to get me that's going to help me incorporate delta t into this expression here, right? So we had dy over dx, the derivative, right, slope of a tangent line. I can multiply this expression here, delta y over delta x, by 1 over delta t, right? Because again, the change in t is not 0 if we have some non-zero change in x. We'll be at different locations. Same thing down here, 1 over delta t. And as I mentioned, delta x approaching 0, you can say is coming from delta t approaching 0. Not necessarily, but like we're just going to focus on that moment. All right. I'm going to change this now to the limit as delta t approaches 0 of, numerator here is now delta y over delta t, and the denominator is delta x over delta t, and each of these separately with, delta t approaching 0 are the derivative of y with respect to t in the numerator, and the derivative of x with respect to t in the denominator, right? Or you could say y prime of t divided by x prime of t. That'll give me y prime, in terms of x. I guess I could have called this y prime of x earlier. And these are pretty simple to find, right? Again, I'm assuming you know some things from calculus, Calc 1. If this is x of t, then x prime of t is simply 2. I'm applying the power rule and sum rule for derivatives. And it's just a line, right? And then if this is y of t, y prime of t is just negative 2. So when all's said and done here, our dy over dx, right, the slope of our tangent line of this curve to this curve, is y prime of t, so negative 2 in the numerator, divided by x prime at t, at any value of t is positive 2, and this simplifies to negative 1. And that's it. This is the dy over dx, y prime, first derivative of this curve. So let me go to back to the website. Now you can see that that is the correct answer, right? dy over dx is negative 1. And let's just verify this with a picture. All right, so I'm going to go to desmos.com. This is a free online graphing calculator site. And I'm going to enter the parametric equations that were given to us. So to enter parametric equations in Desmos, go left parentheses. You have to enter the parametric equations as an ordered pair. So the x coordinate in terms of t was 2t plus 7, comma, and the y coordinate was negative 2t minus 1. And once you do that with the parameter t, it automatically has the range of t be from 0 to 1, so we're only seeing these set of points here. I can make this a little larger. We can go from, say, negative 10 to 10, just to get more of the curve traced out, and it's just a straight line. And I hope it's very clear that this straight line, no matter where you are, the slope of this line is negative 1. So it has a derivative of negative 1, right? We can very clearly see some points here. I'm seeing the point 5, 1 up there, right? You can see that's definitely on the curve, and the x-intercept is the point 60, right, which is clearly on the curve. So even from just those 2 points, you can see that the slope is, down 1, right 1, has a slope of negative 1 the whole time. Derivative is negative 1. Great. So did it by hand, develop the idea of finding the derivative of a curve when your curve is defined parametrically. It's just y prime over x prime of t. And we also kind of verified it visually, right? I do like to try to verify things visually if possible. All right, wonderful. And that's what I'd fill in the blank here, negative 1. Now, if you are working on a problem like this in this Knewton Alta, after you submit an answer, whether you're right or wrong, you'll always be given some sort of explanation for the answer. I would highly recommend reading through those just to make sure you fully understand why something was right or why you got something wrong, and hopefully better grasp the material for next time. Great. All right, so thank you very much for watching.